First of all, maybe I should tell the title. I think Hausdorff maps. Metrization. Explain the title. Okay, metrization is a topological metrization theory. So metrization, maybe I think I have it here. Maybe better. Topological metrization theories are so metrization topological is so far is accountability. Is accountability criterion. Accountability conditions or like first countable, second countable, sigma disjoint, sigma discrete basis. Right, it's a accountability thing, right? Oh, hello. That's topological metrization. So, okay. And this has been quite successfully dealt with to the point that the one of this particular relaxation of second countability, this relaxation of second countability catches metrizability, meaning is equivalent to it. But if you want to go to inside or separable spaces, then second countability catches. Of course, I'm assuming the spaces are reasonable separation, so that we don't need to consider more than it's that can be catched by a metric. And okay, so what I want to do is to get towards a new, I guess, a new type of metrization criteria, which is motivated by basis problems. For a long time, I was interested in the various basis problems, motivated by various basis problems. So let me just, everybody knows like a basis problem for linear order sets is a problem where you can characterize countable linear orderings. Countable linear orderings are characterized by a finitely many forbidden configurations, or this mean. So we are looking forbidden configurations. And the quotation marks. Maybe even more, right? For example, you would like to characterize metric spaces by forbidding certain things. This is still open problems for, say, first countable spaces. There are candidates for this, but we are not yet to the point of solving it. In the classical sense, first theorem, in the combinatorial sense, in a first theorem, I think you should always, whenever you have this always remember Kuratowski's theorem for planarity. That's sort of a, so really combinatorial. So this research, as I said, is for a long time it's a basic problem, but this directly related to the the invention of open graph axiom, open graph principle, or whatever. Because what is that? It's similar as a Kuratowski. There's a homomorphism from G to K aleph 0 or to K aleph 1. There's a homomorphism K aleph 1 into G. So this is countability requirement. Graph is countably chromatic, or whatever you want to call it. And this is a forbidden configuration. Yes. And should this particular work was started by the influence. In other words, that's why actually the first time that I took OGA seriously, because of its influence to gap structure. And let me explain you this and why this is at all relevant for what you're talking about here. Well, why this is a very strong influence, basically essentially telling you there's only three kind of gaps. I mean, there's the obvious gaps, nothing else, more or less. In some sense, in some sense, power set omega modulo phi is as complete as it could possibly be. We know it is not complete, but okay. Yeah. And now, why is this relevant to us, to metrization? But this is exactly this is of the following graph. Let me copy it not to make error. So the following the graph, given point, a point X in a space X. Typically, everything is non-isolated point, space is nice. There's a graph associated. We associate the corresponding graph Gx. What is its vertex set? Is this vertex set of the graphic is it's okay. So well, sorry. No. Well, no. Okay. So I want to relate it to this. So there is a gap, but okay. So let us see. Let us write it AB. A converges to X. B doesn't accumulate to X. And there should be a subset complement of singleton X. Okay. This one is, but this may not. I don't want to consider the trivial sequences. So these are an A intersection B empty. That's a vertex set and edge set. Says that A intersection B prime union B intersection A prime is empty. I guess is non-empty. Okay. That's the graph.
These are all countable subsets of X, A and B.
Well, at the moment you don't think, but eventually you will come to the point accountability thing later on. But this is a particular graph that you want to associate to a point if you want to analyze points using this. This graph is open. By the way, open, I did not even mention it. This is the influence. This is the OGA is actually quite interesting theory because of this fact open. It refers to the descriptive requirement of the edge set. Open in some topological sense, but if you want to think about commutatorily, which I think is a good thing to think, because otherwise you have to worry about which topology which is open, etc. It's simply a sigma bipartite. So that's how we should think of it. Okay, so that's the, and now, so this is the, so this is, and gaps and points. Well, what is a gap? Again, if your space is separable, then you see OGA will have to, it will be influential on the countable index set. Later on, you will get another dichotomy, PhD dichotomy that works for arbitrary, which gives almost identical influence on the gaps. But think about at the moment, what are the gaps to get, but it's written there. I mean, it's the ideal Ix is at full D, so the B doesn't accumulate to X. And Ix, I like to call it orthogonal, although, you know, you can switch the way around, but you know, A converges to X. So that's the gap. And that's actually exactly how the OG was used originally. And this is the partition for the gap. This is actually. And later on, it has been shown that in some sense there are no other partitions. I mean, it's really general in some sense that there are no. Okay, so this is so again, there's a point, there's a gap, there's open graph. So let us see how this is relevant to the metrization criteria. Yeah. How this is relevant. Well, okay, let us go to the theory of gaps. Oh, gaps. Of say a countable index set. Later on, as I said, there's another dichotomy. Gaps in under well, let us see what does it mean. So given a gap is simply two orthogonal families. This is maybe a pre-gap, if you want to call it, two orthogonal families. So this basically means that B is a subset of A orthogonal and vice versa. It almost joined the pairwise. Every A and every B almost joined. The alternative of OGA applied. Again, maybe I should call it, maybe this should be a called, okay. Apply to the open graph. GAB, I guess, where A, B are, A is the thing, B is thing that don't accumulate, and, or sorry, in other words, so this is basically, sorry, A in A, B in B disjoint, And this is the same edge relation. So is it clear, given a gap or a P gap, there is a corresponding graph, correction of all A and B, A and A, B and B disjoint, and the edge relation is this heating, this bioorthogonality relation. Okay. Applied to the open graph, give us the forwarding alternatives, which remarkably are interesting, even if you are not intending to apply principle, which actually are crucial, even if you don't want to apply it. So what is the alternative one? So this is the notion for gaps. Can't we separate the gaps is the following, is a gap or a pre-gap, i.e. there's a countable sequence. There's a sequence, I think, there's a T of sets such that. And now we have to be a little bit careful about here. If your index set is countable, then you don't care. You want them. Well, let me just write such that for every B for all N for all A in A for all B in B. I don't know. There is a C in C. A is and now, as I said, is a matter what you want to do. A is a say subset of C, and C is orthogonal to B. You can switch sets. Can't be separated. It's a very important notion. The important notion from the point of view of a theory of gaps. Theory of gaps. And the two, there is a bioorthogonal gap. Subgap. A cross B is really okay. They are disjoint. Okay, A cross B. So bioorthogonal gap, subgap means that A alpha intersection B alpha is B beta is empty if and only if alpha equal beta. Okay. I think it should be even better. Okay, that's okay. Which is right. This is a complete subgraph of this graph. Right. If they are different, then there's a heating. There's a heating somewhere, right? Okay. Yeah. This is the. Is this clear that the number 2 gives you this? This is the image of the complete graph.
Is the first one also obvious?
Yes. Yes.
The second one looks more obvious.
Yes. The first one is yes.
Also.
Yeah. You take it's a countable union of non-heating. You take the union of projection. There's a countable. You take the projection. These are C and this is a projection C.
Say C and B are orthogonal. Are you mean just that C misses the closure of B, or that the
intersection of A and B, every little A from A and intersects every little B infinite. Orthogonal
No, I mean C and B. You wrote C is orthogonal to B.
Yes, so this C intersection B is finite. Yeah, it's easier to write this because no, there's no topology yet here, but no topology yet. But this is pure combinatorics. Yeah. So this is all. This is in this book, Partition Problem in Topology, where it introduces OGA. Okay, so this is about the gaps. Let us now go towards the definable theory of gaps. This theory of definable gaps. This is a large subject. So in this case, A and B are assumed to be definable, like a Borel or analytic, etc. If you want, say, yeah, okay, then you can do then you are in a definable version of OG, which is actually much simpler principle. It's easier. It's in consequence of this, but nevertheless, what is crucial here is this condition. Countable separation is the crucial condition that distinguishes you type of gaps, strong and weak gaps. So we have various. There are two important. Well, actually, there are now many of them, but okay. There are two initials. Okay, dichotomies for these gaps. The first one is saying definable gap in B is either countably separated or you contain perfect orthogonal subgap. So that's simply the same thing, right? And the other one is actually also very interesting.
Perfect here means just
the image is perfect set. These are subset of the power set, so it's a perfect index. There's actually much more. There's a very nice gap where if you change your index set with a complete binary tree, then there's a very nice gap there, orthogonal gap. 0 chains and 1 chain form a very nice gap. By the way, speaking about this, realization of this could have fortunately people did not realize this 100 years ago, because otherwise Hausdorff would not have invented his theorem. If he noticed this orthogonal gap, which is definable, then he would prove the power set omega modulo phi is not complete, and that's enough. So basically, every one-to-one sequence of reals gives you that two orthogonal family or size alpha that cannot be separated. So remember, the Hausdorff gap requires much more choice than this. This requires just omega one sequence of reals. Okay. But anyway, but the gap there is definable, and it's basically you can actually, there's embedding of this gap there, whatever. But the other one is actually interesting as well. Into this, if A B is definable, say analytic. No. If A B is a pregap, and A analytic, not necessarily B. B can be arbitrary. Then either A is can't be generated in B orthogonal, or there is embedding of the or the A, B, and B contain a copy of this gap of on the index set on this index set on gap on rated of all things. So again, the B is collection of immediate successor of nodes of the tree, and A is a collection of branches. So particular gap, big gap. I also should warn you that in the theory of gap, because of this, we are interested in the separation, counter separation, etc. You are allowed to mix ideal not to be really ideal. Yes, and you are allowed to cheat and say, I just go to a subfamily of your ideal which has the property that every infinite set in ideal almost contains one set in the families, because they are the one that determine whether you can separate or not, right? Because sometimes okay. These are and one of the things which one of the things that I realized, and I was rather happy at the time, these early 90s, is the Hausdorff phenomena. So if
How generated things can't be separated, or
no, counter generated is stronger.
what does it say?
That there is a countable sequence of elements of the orthogonal that almost include everything in there. There is you don't care, you don't know.
So it doesn't have
Yeah, it doesn't need to. It's a stronger notion, but of course it's very closely related. Notice that if one of them is a p ideal, then this is the same thing.
I see that.
So they are really relatives to each other, these two dichotomies. But of course, the first one was proved this, and this is refining this, because in other words, you are not particularly interested, or you cannot find, you want to have a better gap than this, more informative gap, and this is this one, on this. Remember, you are interested in the basis problem for gaps, so you are interested in what are the more. And what I was particularly happy that if A and B are two orthogonal P ideals, and if one of them is analytic, then they can be separated. Right? Because you applied this B, there would be a P ideal if counter-generated orthogonal, so it's really one of them suffices to be in between, right? So this is obviously this. And so which means the Hausdorff, remember, the Hausdorff got the two P ideals that cannot be separated. So there's no definable, the Hausdorff theorem, remember Hausdorff theorem, there is omega 1, maybe we call that Hausdorff early. He reproduced in 1934, but I think it's early 1911 or something, originally proved. That there exist two out of one generated, two orthogonal out of one generated P ideals, which can't be separated. And this particular is called Hausdorff gap, right? It was the Hausdorff gap, because he invented, of course, this is rather obvious under CH, right? But he invented a condition that guarantees you in ZS. It is this Hausdorff condition, which actually going to show up in today's talk. Exactly that condition. As a for is forbidding this gives you metrization. Okay. This is the Hausdorff condition. I will recall you the A alpha, B alpha. Ah. The orthogonal, I guess you can also write it like that. And the more important thing is for all beta, for all n, set for alpha less than beta, A alpha intersection B beta subset of n is finite. This is this remarkable condition here. Okay. This is that. Another thing which I should have mentioned in the previous paper, but I mentioned that the paper which a year or two ago, afterwards, I think is number 4, the orthogonal. Of every analytic p-ideal is counter-generated. P-ideal I is counter-generated. So, yeah. Okay, so this is that OGA gives you that sort of a thing. And now we go back to the metrization. The first was done in the context, so we are now in metrization, we are interested, of course, it would be great to have corresponding, but for the moment, we concentrate on that. This is metrization. This is the first compatibility in the context of general spaces, or metrizability in the context of topological groups. We will first treat that. And this was first discovered in the context for definable in the paper, of Baire class 1, compact set of Baire class functions, in the paper where they solved the basis problem for these compacta, as well as their points, particular points. And which mean the first contributor. This was the observation that in the particular context, which is a compact set of Baire class 1 function, if you apply the OGA to this, even though when you think about it, you really can't apply it. But anyway, if you apply it, you'll get a very interesting thing, that the countable separation and the other alternative gives you so this is the Tukey and gaps. First realization that the Tukey theory and gaps are closely related. Okay. And this is maybe so far I'm talking too much, so you want to hear a theorem. So why don't we hear a theorem and then talk about it rather than a history? And here's a particular theorem. Okay, so Tukey shows up in the if you have a bioorthogonal gap, then in particular space, say complex set of class 1 function, bioorthogonal gap, say perfect bioorthogonal gap, you'll get it's telling you that your point is a neighborhood filter of your point that has a Tukey top type, has a maximal Tukey type. This was first realized by looking at this gap and applying the dichotomy and doing something, a little bit of infinite dimensional Ramsey theory, which in the context of a perfect bioorthogonal gap is you can apply and was very fruitful in other contexts. For example, using this was the separable quotient problem was solved in the dual spaces using exactly this sort of ideas. But okay, let us see what is so I recall the Tukey reduction. I think there is a F from D into E mapping unbounded sets, unbounded sets. Or vice versa, there is a mapping recurrent in this mapping G from E into D mapping for final sets. For final sets. Okay, it's a very fruitful comparison of directed sets and even other posits. So we are interested in the abstraction to countability. Tukey abstract, we are interested to Tukey abstraction. To first countability. That's what we are interested in. Why? Because the neighborhood filter of a point is the directed set, right? And we know what the first counter will say. So so if you have a point x, you have a point x, so the neighborhood filter of nx or f or whatever. Let's see if we want to stay in the ideal. So ix set for a subset of x minus x. I call them their b. B doesn't accumulate to x. That's equivalent. This is a neighborhood ideal. Complements a neighborhood. So first countability. If and only if ix is less than omega in the Tukey sense, right? That's this. Okay. So what's the abstraction? What's the other alternative? That's the one. And somehow we are looking Ogier to help us to guess, right? And now the question is, why Aleph1? Why directed set of alpha? Why not Aleph7? That's the problem, right? Because it's arbitrary. We are talking about arbitrary point in arbitrary topological space. So we need to figure out what are the good. So we are interested. So question is, so the question. Well, let's put it on this board here. So this is an important question to think about in every other context. What to put? What are the possible Tukey abstractions? Question? Corresponding. Maybe not one, there may be more than one, right? What are the corresponding to abstractions? For example, we are interested in the Ix or D for some canonical, some vector set. Okay. So that a point is first countable if only if there is no, if D is not a Tukey quotient. That's what we did. Of course, there are, as I said, you have other things. For example, first countability, you can, it's not just a Tukey, because first countability has many other things. So before we get this, recall that.
So this is two key abstractions for first countability.
Yes, exactly. We are looking for that. What are the all? So what is a two key abstraction and what are all abstractions? Hopefully we find a finite list, right? Because you don't want to have an infinite list. Remember, you want to solve a basis problem for the. You want to solve a basis problem for a non-first countable. Right? Don't find a. Yeah. One of them would be one of them is two key. The other one are not so difficult. The other one is X must be crochet point. If it's not per sure, there's a thing, and then obviously something like that. As a matter of fact, it should have a strong diagonal shape. X should have a strong diagonal sequence property. Recall there's an array of these ones, but the strong one is, I think, is the first one. That's, I think, maybe stronger one. That you can, you have a sequence, if you have a sequence or converging sequence, then you can chop off piece from each, find a piece of each to get a converging sequence. And now it comes the other principle which gives you similar theory of gaps, and in other words, you need here this one. Of neighborhood filter, of the neighborhood filter. So we found the canonical.
Not a two key quotient is the same as not.
Yeah, not below, doesn't. Yes. Yeah. Okay, so there's the. Let us test how good this result is, because remember you can have a lot of. Let us test this. We are going to test it using topological groups, because first countability in these groups are the same as the metrizability, and it's easier to get sense of what's going on. Recall the group is metrizable if the identity is first countable. So what are remember we are interested in the Frechet groups. What are the Frechet groups? Well, we have examples. Or the Tikhonov topology. Tikhonov. Well, product topology, I mean, the pointwise topology. The topology of pointwise converged. Tikhonov topology. That's the Frechet group. As a matter, even it's Frechet even if you put a countable here. Yeah. Notice that is typically, unless it's trivial, is not if theta is large. Is not metrizable. But obviously there's an obvious Tukey reduction. Obvious Tukey reduction. Tukey reduction of this one to the neighborhood filter. Maps singleton to singleton, I guess. Restriction being zero there. This particular, and then you find a set being zero on a particular final set. There's a neighborhood of the identity, and it's a Tukey reduction. And what about alpha one? We already know, of course, the group is not alpha one, is nothing, but there are two results, right? What about separable? Frechet groups. Why I say countable? Because it's related to alpha one. Alpha one is count many converging sequence. This is the countable set, group generated by this countable. If this is metrizable, then obviously it's like alpha one, right? That's the reason. And there's two results. One mine with two results. With Vuskategi is countable. Is a descriptive theorem, ZFC countable group, Frechet group is metrizable if only if it is analytic. Its topology is analytic. This uses these dichotomies, defined by dichotomies of that. And there's a beautiful result of a Hrushak. And now I hope you can help me with it. You can probably help me.
Start. Mine is the same place yours is.
Well,
if you hadn't asked me, I would.
yeah, okay, sure. Garcia Ramos, right?
Garcia Ramos.
So this is a Frechet group. It is consistent. That separable or countable Frechet groups are metrizable. So which means that if you look at ZFC examples, all of the groups are going to be alpha one. If you look at the Frechet group, you're not going to find one that's not alpha one in ZFC. Let us look at some examples. new examples. Well, I want to vary on this. Another example. Regular, uncountable, cardinal theta and square theta sequence C alpha less than theta. This is the sequence. C alpha is a club subset of alpha coherence property, and is not can be thread. It's not trivial. Yeah, for example, square of omega 1 is true. There's the one instance when it's okay if you don't want true. And let rho 2 be the step number of step function of the walk. Function that counts the number of steps of alpha step alpha beta from beta to alpha of step of walk from given beta to alpha less than beta along the about the seed sequence. And this is the group 0, 2 theta. This will be again the finite subset of theta, group arranged for semi difference, and the topology generated, neighborhood generated by the following sets. U beta n less than omega, beta less than omega. So topology, neighborhood basis of identity generated by this. Set for finite sets for all psi in X intersection beta, rho 2 psi beta, about n. Very natural. This is always alpha. So claim 0, 2 theta is crochet alpha 1. I mean, the empty set, its identity is alpha 1 group. And now the question is it metrizable? And it's not, which is not metrizable.
But these are the neighborhoods of data.
Yes, these are the neighborhood bases of the identity. Topology, and this is why I put this, I guess. Yeah. And now, what are the Tukey type of the neighborhood filter? What is Tukey type of the neighborhood filter? Whatever it is, has nothing to do with this. Whatever it is, has nothing to do with that. Okay, so let's see. Why, this explains why omega 1. Like if D is directed is a directed if D is a quotient, this if the directed set is a Tukey quotient of the neighborhood filter of identity of the G2 set of empty. And generality of D is less than theta, then this control cofinality. There's only trivial things below. The only trivial small things. So the question is, so which means if theta is large, we contradict the theorem. But of course, hypothesis, which means the P del dichotomy kills square, which is known. Okay, so what about theta equal omega 1? Because this is a ZFC. What about? Because in this case, C sequence exists. And this theorem will tell you if you want to go in ZFC, that group is going to have this is a quotient. Right? And the theorem. And myself recently in 2005, if C alpha is then this is not a Tukey quotient. Of course, it's not metrizable group, so yeah. True of this, of course. By the way, for groups, you write this is the neighborhood filter of identities. Just a simple way, right? Okay. So which means that this is not a ZFC fact. Yeah. And in some sense, this Todorcevic thing is a natural thing too. Yes?
Equivalent to Tukey to omega times omega 1.
No. This, okay, good. So this is good because there was that Tukey lattice. So that's where you are looking for, there are these Tukey lattices. The lattices which Tukey originally invented. He observed the obvious directed sets of particular size up to LFN. And he was asking, are there other? He noticed that for LFN, LF0, there's only two, which is a 1 and omega. For LF1, I proved this is actually the PI dichotomy comes from that PFA implies the T1 is a T1. So Tukey lattice. And that's that's actually a very good question because you have a Tukey lattice, you have a group, and you see what is possible and what's not. And this has been cleared up. A good question. So in omega 1, okay, T1, Tukey lattice 1 is this. This is the top one. And there is an here, this is the place where there can be many things in general, but So this is okay. This is simply a first continuity or whatever is isolated point, first continuity, non-isolated. These and these are not possible. So meaning the one is the other thing. Okay, good.
You say not possible means as a Tukey type of a.
Yeah, oh yes, no, yeah.
So it's either omega or the top?
Yes, exactly. It's either isolated point, omega. Okay. And now I finished this paper and there was a Borovac meeting. I forgot, a year ago. And then Mike Hushak was reminding me of a question, which I somehow I feel that I know the answer because I simply forgot everything. He asked, he was interested in a very general topological metrizability. He was interested, which of course I was also interested, but I forgot that I was. Criteria. So now is the new subject. For ideals on ideals I on the countable index set. And which topology? This is exactly one interesting topology. So the topologies are given. That's how I be the, and now I always am mixing things, maximal or minimal. I think it's the maximal. Basically, you give us a set of converging sequences, and you only take the maximal topology that respects them, right? It makes sense that like in maximal or the minimal, right? Because otherwise you can kill. Yes. So yes. So maximal is be the maximal. I don't need to look at it, perhaps. Yeah. Such that every sequence xn now since okay, well, every sequence xn such of I converging pointwise converging to x in I is tau I converging provided union of xn is in I. Why so this is actually familiar. This is the basic orders topology. There's an offer basic order, and that's exactly the topology. Right. But of course, you want to get abstract metrization criteria for that, right? What are the examples? So the question is, which ideals are? Question is. Well, there are examples. I think they rediscovered some of the examples that I knew actually even published. There's one that everybody knows, which I think this is first point. This has been first pointed. If you just please, you should correct me if you find earlier reference. I think 11. If I is non-eager p-ideal, then Ti is equal to pointwise, and therefore metrizable. It's a standard fact. So it's probably difficult to find. You put it this way, but if you put it that way, it's probably difficult to find. The way we said there, it's a basic order, which is a cool. Anyway. Okay, let us see another examples. What about another example? This one is very famous. Is the definable version. If I is an analytic p-ideal, then this is of course reading result. Of course, you also have to read different. It's a basic order, whatever. Then Ti is metrizable. Okay. These are standard example, you know.
For the first one, I mean, isn't that really like Galvin or something?
Oh, that would be great. Find me reference and I'll feed. Okay, so let's try to get it. And this is where Hausdorff shows up. See what is the time? Yeah, we have time. Very great. And let us see, you will see the ideas of the proof, and you're going to see that almost every move and every definition that we had so far is crucial. In a theorem, a metrization theorem for the, which implies all this. All known things. Yeah. By the way, why p-ideal show up? Because it is not p-ideal, it is non-metrizable, right? Because pairs diagonal sequence properties, so sequence converging sequences, there must be a. Okay, that's kind of clear that if something is not a p-ideal, it's not metrizable. So. Or we are going to leave this because we're going to show up. So now we're going to start with fixing a p-ideal I, and I'm going to see what are the obstructions to metrizability. So remember, metrizability is about the gaps. And which gaps is here? But natural gap, right? So such a thing that converges to zero and the thing orthogonal to it, right? We analyze the corresponding gap. The gap associated to the point of I in this topology, right? So remember what the gap set for things that don't accumulate to the points and the set for things that converge to the point. These are the two. Yeah. And so it will help us. We first reduce the index set. Remember, like in the case of remember in these results of which I mentioned, it's still on the board. My result with Buscattegui and Hushak and Garcia Ramos. People sometimes say it's about countable groups or separable groups. The same things. The same thing is happening here. We want to reduce ideal I to some countable object. And why we can do it? And which countable object it is? Finite sets, the correction for finite sets are dense in this topology. Finite sets are dense in the topology. So that's a natural thing to do. And also notice that if you have a sequence that converges in it, this is a complement in the ideal, right? You take a thing that almost includes everything. This is the boundless thing you could throw out. Then now where this converges in the new topology depends on these finite sets. So you see what I'm saying. If you have a sequence of these sets Xn, if there's a Y that almost includes them, that is a finite, then this is bounded by Y. And of course, they are still going to converge to whichever you can bound. Of course, you can bound Y and the limit X. Y can be. So therefore, it just matter where the sequence of finite sets converge in a tau I to empty. That's the matter. That's what matters. That's exactly. Set for sequences of finite sets Xn pointwise to empty, and the union of Xn is in the ideal. That's this is actually orthogonal too. So I now switched. Now notice, by the way, why can I switch I and orthogonal? Why? Because orthogonal is itself, so I can switch. Although you have to be careful when you reformulate this in the metrizability criteria, meaning that we are not interested that this is 2k less than omega. We're interested in the orthogonal, so that we are interested in the CI, which is orthogonal. This is essentially 2k the same as the neighborhood filter of empty in tau I. So that's what we are really interested in. Countability of that. Yeah. So we are interested. So metrizability of tau I is equivalent to CI orthogonal less than 2k sense omega. Right. Because these are the things that don't accumulate to empty. And every set, yeah. And now this topology is difficult to analyze. To move from a hardly T1 to metrizable, you have to work, right? Because the topology is very strangely given, right? It's not. And okay, so this is a theorem, and then we go we're interested in interpretation of this theorem. Is there something there? Okay, yes. is metrization or this doesn't show up? And now you have to be careful. Now the order is important. The order AB, now AB becomes important because of this stick here. So let's see. Well, I better copy what is here, otherwise I get confused. So there's a Hausdorff gap in this, and then we go to a Tukey in a similar manner. See, that's the, how did I denote this? Okay, so basically, by the way, this is also about, this is about the empty, so you can put here empty, but let us, these are about empty. Any other point would work as well, but so I can ignore this. So there's a Hausdorff sequence there. And now it's very important order. Very good. I guess usual thing, A alpha intersection B alpha. Ah, no. We have to avoid the other thing. B, there's the metrization theorem, and of course the Tukey corollary. Where the Tukey corollaries, if you want to work in the Tukey. It's very similar to the
Yeah, is metrizable? There is a sequence.
sorry.
Oh, means you mean not metrizable?
Mean not metrizable.
Yes, I guess for every if only is okay. is there's no there's no sequence. Thank you. You can also figure to say that this contains no Hausdorff gap. Notice that the Hausdorff gap has a. We know that the CI is a p-ideal, but we don't know where the other one. We don't know where the other is a p-ideal, so we don't know where A alphas chain. But it's interestingly the fact that the B alpha chains is exactly responsible for Tukey reduction. And this is what this is this. If I is a p-ideal on omega, then I is a metrizable topological group. Unless, okay, so omega is a neighborhood filter. I don't know how to filter neighborhood filter of the empty set allowed to the TI. And what perhaps more interesting, this, because remember, you took the I, you build a superstructure on it, which is the topology, which is again another group, another neighborhood base. It's a big structure, right? Of course, you're interested. The question is whether this is metrizable. Of course, here is your thing. And now, why you see where is this Tukey reduction here? Of course, the see how it is done there. Remember, orthogonal to I said is the same as the neighborhood filter in the Tukey sense. So A alpha singleton A alpha goes to a singleton A alpha goes to a singleton A alpha as a Tukey reduction. Exactly because of the B alphas are increasing modulo phi. So every infinite set is unbounded of the image. It's exactly of that. Because if the image of infinite set there is bounded, that bound will be homogeneous from the B beta in the index B beta. But the homogeneous will be N, which captures this, and then you fail the Hausdorff condition. You fail this condition 3. This is that Tukey reduction. And the other one is actually interesting because it shows up the difference between the definable world and this. This one is useless if CH is true, because everybody is. It's not counted with cofinality, the omega 1 is. But in the definable world is as strong as that. Right. So this is all interested for definable. Okay. And now have a few more minutes to give you which gives so the key lemma for the proof. If the gap now what was the notation? The converging sequence of the relative bounded converging sequence. Bounded converging sequence and this other one. If this gap is currently separated Well, if and only if I think the gap is currently separated. If and only if, whatever I wrote there. Tries the topological group. So which means that in the proving this theorem, you would not know where to start if you did not have this notion. Right. And what is this notion is giving you? What is this notion giving you? Exactly something to help you analyze this strange topology, which means to go to a powers, to show that the union is a continuous map. So key lemma or and a sub-lemma of this. Okay, I can keep this idea. And another key lemma to that. If the gap, if Ci is currently separated, the point empty of I is not only Frechet, but also bisequential. This is exactly what was happening in this definable Bayer class 1. Exactly this bisequentiality was crucial. Bisequentiality, unlike Frechet, preserves on the powers. And that allows you to show that the union is a continuous map. And this is a topological group and a neuron. So this thing. We can breathe 55 seconds if you like, or ask question. I'm done.